Welcome to class number 2 of our Commercial and Industrial Refrigeration course. In this lesson, we will study the main types of piston compressors used in domestic, commercial, and industrial applications. To begin, we will review the fundamental definitions and concepts related to this type of compressor. Piston compressors are the most common in the refrigeration sector. They operate by confining and compressing specific volumes of gas between the piston and the cylinder. The reciprocating movement of the piston allows the refrigerant to be drawn in during the intake stroke and expelled during the discharge stroke. The suction and discharge valves, operated by springs, open and close automatically as the piston moves inside the cylinder. These compressors can be open, hermetic, or semi-hermetic. In all cases, the motor rotates a shaft that drives the piston. This movement causes the intake valve to open, allowing the suction of refrigerant vapor. Then, during compression, the suction valve closes, and once the required pressure is reached, the discharge valve opens to expel the compressed gas. Among the main advantages of piston compressors are their high durability, repairability, and excellent performance in systems that require very low temperatures, where multi-stage compression is especially convenient. The types of piston compressors according to the cooling capacity regulation or control method are fixed-speed piston compressor with on-off control, variable speed or inverter piston compressor, piston compressor with unloaders or digital compressor, piston compressor with thermal load simulation through hot gas bypass to suction. 1. Fixed-speed piston compressor with on-off control. These compressors regulate their capacity by turning the motor on and off. When the space reaches the desired temperature, the compressor stops. When the temperature rises again to a defined value, the compressor turns back on. They are mainly used in low-cost and small-capacity equipment, where investing in more efficient technologies does not represent significant energy savings. 2. Variable speed or inverter piston compressor. This type of compressor controls the amount of refrigerant that circulates by varying the motor frequency. It does not turn off. Instead, it adjusts its speed according to the thermal demand, allowing much more precise control. Its main characteristics are: cooling capacity is proportional to the motor's rotational speed. Frequency variation allows the cooling output to adapt to the system's real demand. Improves evaporating pressure stability and reduces temperature fluctuations. Offers greater efficiency at partial load. Extends compressor lifespan by avoiding start-stop cycles. Requires very low starting current, avoiding the need for auxiliary devices. Reduces risks of sudden liquid or oil return thanks to gradual speed increase. Has a minimum frequency that ensures proper lubrication. Modulation is achieved through frequency steps, for example, 30, 38, 46, 54 Hz. These units are more complex both mechanically and electronically. 3. Piston compressor with unloaders and digital compressor. Both methods reduce capacity by temporarily disabling suction in certain pistons. The main difference is that unloaders work in capacity steps, while digital technology modulates almost in real time. Capacity control using unloaders. This is used when the thermal load is lower than the design load or when ambient temperature is low. Without capacity control, the compressor would operate at excessively low evaporating temperatures, creating frost on the evaporator, low humidity, and risk of freezing the external fluid. Reciprocating compressors of more than 10 tons often include unloaders. These adjust refrigerant flow by blocking the gas inlet to certain pistons using a solenoid valve. Although the piston continues moving, it no longer compresses gas. When the load increases, the solenoid closes and suction is restored. Operation in 6 piston compressors. In a compressor where 4 of the 6 cylinders are equipped with unloaders. Under design conditions, all 6 cylinders operate. If the load decreases, the first pair of cylinders is unloaded. If the demand continues to drop, the second pair is unloaded. Once the minimum suction temperature limit is reached, the unit shuts down for protection. This system expands the stable operating range at partial load. Digital reciprocating compressors, Copeland Discus Digital. The Discus Digital series uses 3 cylinders and continuous modulation without a variable frequency drive. A special solenoid controls a piston that regulates the flow of gas to the suction area, preventing refrigerant entry when compression is not required. Main characteristics are continuous modulation from 10% to 100%, economical and reliable alternative to variable frequency drives, excellent evaporating pressure control with greater energy savings, easy integration into new and existing equipment, fewer vibrations and mechanical stresses, reduced number of starts and stops, extending compressor life, avoids current spikes and electronic interference, high efficiency due to its low clearance volume. 4. Piston compressors with capacity control by bypass or hot gas diversion to suction. In this method, hot gas is recirculated from discharge to suction. Important: this type of control does not reduce the compressor's power consumption. It only reduces the effective cooling capacity. Effects: the compressor continues operating at 100% power. Cooling capacity is artificially reduced. Used when short cycling must be avoided. The evaporator operates with highly variable loads. There is a risk of liquid return to the compressor. Common in industrial freezing equipment, ultra-low temperature systems. Common mechanical problems in piston compressors. Flooded start. Occurs when refrigerant migrates to the crankcase when the compressor is off. The liquid mixes with the oil and reduces lubrication and causes wear. It is prevented with functional crankcase heaters and proper piping traps. Liquid refrigerant in suction. The compressor must receive vapor only. Liquid entry may be caused by control failures, too many compressors running, expansion valve issues, or sensor failures. The solution depends on verifying these components. Low suction pressure may result from refrigerant leaks, insufficient charge, dirty evaporators, poor air circulation, poor adaptation to partial load, or incorrect equipment selection. High discharge temperature, commonly caused by excessive compression ratio, thermal overload, or condensation issues. Lubrication failures may originate from deficiencies in oil traps, separators, lubrication stations, or poor installation practices. Verifying pressures and oil levels is essential.